Good morning, everyone. I think I've got like a lot of pressure to finish my presentation in time. I could see 15 minutes, so I'm gonna try that. Yeah, so there's a little bit of shift in the topic. We know in the last discussions panel, it's all about reclamations, coastal risk and things like that. So I'll be talking about buildings at this stage and the foundation. So a little bit of background. I think I want to take advantage as well to say that Happy International Women in Engineering Day. Yeah, I could still see a lot of... So I've been, like my experience runs over almost 2 decades now. I've been in the region for 18 years. I'm a mother of 2, so you can imagine how tough as well my career journey. I'm a fellow of the Institution of Civil Engineer. And yeah, my focus of the career that I have circled within advanced geotechnical analysis, value engineering, and foundation optimization. So I will be presenting a case study, which is very specific, and I would say one of my favorite projects that I worked with in the region. And the challenge that we have is basically, can a raft foundation replace a conventional foundation system in the region? So when we talk about mid-rise to high-rise building in the region, we automatically think it's going to be piles. It will be supported by piles. So therefore, in terms of thinking beyond what pile can provide or what the foundation can provide in a certain building, we look into a particular impact, which is reduction in foundation cost. So let's see whether this case study will answer the question that can the raft replace the pile or the conventional foundation system in the region itself? So case study. This is one of the buildings in Kifap development. I'm not sure whether you're aware of Kifap. It's basically near Sabil Park. We did this in terms of the type of contract. It's a traditional design development stages. And it comprises of 2 170-meter tower. And it's connected by a link bridge. You can see the right image there. That's how the building looks like at the conception. So these are the typical features of the building that we did. You can see there's common basements. It's a little bit deep, 3 levels. We've got 6 levels of podium, which is quite typical in the region as well, and 2 45 floors building. At the top, it's connected with a link bridge. You could see there's a pool on the top as well. So you can imagine the differential settlement requirement for this building. But my title of the presentation talks about mid-rise. None of the standards, I would say, define what mid-rise is, what high-rise is, up to tall tower. So if you look at Google, if you ask Google what those, how do they define different towers, we can say low-rise, it's about 1 to 4 story, mid-rise 4 to 12 stories, high-rise 13 to 40, and when you start talking about more than 40-story buildings, it's called tall buildings. I'm not sure whether you're aware of Council of Tall Building and Urban Habitat. They define tall building whenever the building becomes too complex to design. So given that this is 170, 45 floors, shall we say this is tall building? Maybe others can argue it's a high-rise building, but it's not a mid-rise building. So I just wanted to set straight the complexity of this tower, and it can be called a tall building at this stage. So engineering framework, basically, this is the, I would say, short representation of the workflow that was considered during the development of the design of this project up to construction. So for those who were here yesterday, we talked about over-conservatism when it comes to ground geotechnical parameters. And that's where I highlighted the fact of understanding existing ground condition or data, and then targeted site investigation before jumping into modeling. So in this case, an advanced 3D modeling. Obviously, design approval from the authority perspective and the construction verification. You don't stop by doing the design per se. You go above and beyond understanding what the actual response during the construction will be. So let's talk about a little bit in terms of site investigation. We took advantage of all available information that we have. And this is what I said yesterday. It's very important to understand the geohazard present on your site, as well as take advantage of what positive notes you can get from all the existing information. And one of the things that we got is the confirmation of ground conditions. After the understanding of the ground investigation, you would then be able to design your additional testing to comply with the authority standard, as well as to increase confidence in designing the building itself. And that comes with the ground characterization. Then after, you go for the design input, which is what you're going to be using in your analysis. So the key engineering decision here is that we did optimize the quality of ground parameters. We don't just go for quantity. We've understood what the foundation or the building requires and how we can go above and beyond to think about the pragmatic approach and obviously a safe foundation design. So in this case, I think I will jump into this presentation in this particular slide, just so everyone understands. We've understood the consistency in the ground model. So we basically understood that the rock head doesn't vary a lot across all the information that we have. Now, going to the context of the building, we've understood that it's 3 levels of basements. So when we plot basically the conceptual level of the foundation, that's where we saw that actually the founding level is right next to the rock head. So this is an important aspect, or I would say the initial study that we did at the beginning, at the concept, to identify how we can make the foundation safe and optimize at the same time. So this is a collaborative effort between the geotechnical engineer and structural engineer at the time, because we come together and say that, can we use combined piled raft system in this case? So that was the beginning of everything. We then designed the ground investigation to focus on the soil stiffness of the material rather than strength, because we know that we need to understand the settlement. And then we jump onto the 3D modeling. But again, before jumping onto the 3D modeling, it's not as straightforward as like, okay, what does your 3D modeling output will give you? It needs to be understood in, like, let's say, olden days, how you hand calculate the settlement, how you hand calculate the capacity of your foundation, such that when you do your 3D modeling, you already know exactly what you expect as a result. You know exactly that whether your result is going beyond your expectation or your initial assessment that you set up during concept. And it's important to set the objective of modeling, which is, in this case, we need to predict the realistic foundation behavior. I think I'm going to go very quickly. We have 5 minutes. But it's important that soil structure interaction is carried out together with the structures engineer. This is, I would say, a different approach that we did, or a more advanced approach that we did in the 3D modeling. You could see that this is a snip of the Plaxis 3D model that we did. We've modeled the tower considering the equivalent stiffness. So we did have our own calculation of mimicking the stiffness of the superstructure. This way is trying to reduce the gap between the structures and the geotechnical modeling. We have the basement elements, structural elements, which is the columns as plate elements, as well as the slabs you can see, but these are weightless, so there's no double counting of the load itself. And the foundation raft is modeled as volume element. Very quickly, just the final results that we got. Obviously, we modeled multiple load combinations. We checked multiple construction sequences to become more confident in terms of understanding all the behavior of the foundation. But you could see that the maximum settlement that we have here with uplift, or basically during the watering is turned off, we're having about 38 to 40 millimeters within the tower. We've also noted the effective stress. It's about 200 to 600 kPa with some localized peak of 650. And this is an example of the springs that we take as an output from the Plaxis and provided it back to the structures. Also, we don't stop from understanding the settlement, how we provided the springs. We also understood the shearing capacity or failure, factor of safety for the raft foundation. You could see that without uplift, or it's during the construction or during the watering, we have about 15 as factor of safety, and it reduced to 13 for during the final or the long-term condition. This is one of the examples how we did check every conditions, every sequence with the structures. We provided the Plaxis settlement, and they check both ETABS and SAFE, whether it provides similar, or let's say a conclusion of convergence between structures and geotech, and check the differential settlement. So I don't want to give all the conditions, all the load combinations, but this is how we basically did all the scenarios. Yeah, so we compared as well the stresses, and it's comparable, and authority approval. So very quickly, it's important that what we did differently in this case is we engaged with the authority at the very early stage. Even at the beginning of understanding what the site investigation needs to be as a minimum, they were there. So we presented the project, we took their requirement, and one of the things that they required, like we didn't get an approval, basically. They rejected it straight away. But they have set out the conditions, what we can do in such a way that, okay, you can go for raft foundation. One of the things is to get a third-party site investigation contractor. So not just one, but we needed 2 site investigation contractors that will basically conclude the same thing. So obviously, like they always rely on the soil report. What is the value of the allowable pressure? What is the allowable settlement, things like that. It cannot go beyond it. So we've got 2 soil investigation contractors report, basically providing the same conclusion in this case. So I'd like to highlight that this is a very collaborative project that contractors came together, consultants, multidisciplinary approach that will make this project a success. Now, performance verification during construction. These are the key things that we did. Obviously, there's a lot. We did full-time supervision in this case. But the first thing we need to understand whether our key assumption that the foundation is within rock is true. So we did the site inspection. I would love to show some photos of the people that have been involved in this, but I kept it confidential. One of the structural engineers here, Akram. I should have shown your photo, actually. But yeah, you could see that the rock the foundation material is confirmed as rock. We did zone load testing, multiple zone load testing just to verify the allowable bearing capacity. And obviously performance monitoring, which I would highlight settlement markers, for example, settlement monitoring, and it showed that our theoretical settlement is basically more than what is the actual. So we've covered about 35% less settlement than the calculated one, which is a very good condition. So just some examples or photos of the zone load testing. And key takeaways: can a raft foundation replace conventional piles? But let me correct this: tall building, and the answer is yes. Key takeaways: better ground data, less conservatism, high confidence. Better engineering decisions, take advantage of the knowledge on the approach from the 3D modeling, and it will give you a better project outcome. So if you happen to pass by Sheikh Zayed Road near Sabil, you can say hi to the tower. It's built, and it's functional. That's all. Thank you.